Hi, this chapter or this module is about steady state heat transfer. The prerequisites for this module, what I would absolutely like you to know is this. You must have had seen this equation, which we call the heat equation, and not only that, you must have known how this equation was derived and what each term of this equation mean in physical terms. So not just math, but in physical terms, what do these terms stand for? For example, the first one is about storage or transient, the second one is about convection, third one is about conduction, and the fourth one is about generation. How does this chapter relate to other chapters? So which other chapters are we talking about? I'm talking about a textbook that I have written called Heat and Mass Transfer, a Biological Context. But these chapters are also similar in most other textbooks. But in the Heat and Mass Transfer Biological Context book, these are the chapters. The first one we talked about basically is energy balance, and then the second one is things like Fourier's law and other laws for various modes of heat transfer. And so we combine this in chapter 1 with the Fourier's law, the energy balance in chapter 1 with Fourier's law in chapter 2 to reach this general equation of heat transfer that I just showed in the previous slide. Okay, so that is the general equation, and we're going to do special cases. So the first one, the simplest one, is this steady state and without any flow. So without flow and steady state. So that is chapter 4. That's what we are about to talk. And then we have other chapters like unsteady state, heat transfer, and also convection heat transfer. Okay, so first, just few introductory comments about what do we mean by steady state and how do we reach steady state. So steady state is different from equilibrium. I often gave these kind of pathetic example that right now my body is in steady state with the surroundings. Whereas if I am to die, then my body would reach in equilibrium with the surroundings. So let's see what we mean by steady state. So we know the energy balance is always true. In minus out plus generation equal to change in storage. If we think of a control volume like this one, then this has to be always true. So what is meant by steady state? At steady state, temperature does not change with time. T is not a function of time. In other words, if the temperature increases, then this body here stores more energy. So it has a change in storage like this one. But because temperature does not change, there is going to be no change in the storage. So this term is going to be 0. Likewise, if the temperature goes down here, then it has less energy. That is also change in storage. And we don't want change in storage for steady state. So steady state means temperature is constant and the change in storage is 0. So let's look at two cases. One is without any heat generation. So without any heat generation, this equation then becomes this guy. Energy in minus energy out is equal to 0. So the discussion is how we can satisfy that. So for example, an obvious one is, let's say, brick wall of a building who's maybe heated inside and cold outside. So there is heat transfer and it's steady. So there is energy into this wall and then energy out of the wall that makes it steady. Another example with generation would be something like this. So this fish that is cold-blooded, but it still generates some heat inside its muscles. So that heat that is generated then comes out through the surface. So the generated heat would be balanced by the heat that goes out. So there'll be net amount that is going out. So we can ignore the in because there's net amount that's going out, and that will keep the energy generated in balance, and together then it can reach steady state. So those are the two examples of how things can reach steady state. So are there conditions when this in minus out plus generation, in minus out plus generation equal to change in storage just cannot be satisfied? So there are things, there are situations when we cannot reach steady state. So for example, if it is just heating of a solid body, then we have just the in term, there's no out and there's no generation, suppose. Then for steady state this would have to be 0. So our equation would be in minus in equal to 0, which is not possible. If there's a net amount coming in, positive amount, then I cannot satisfy energy in equal to 0, which means this will not reach a steady state. In a very similar way, if this is only cooling, then there is only net energy out, and I cannot satisfy this equation energy out equal to 0, obviously, because energy out would be a positive quantity. So there are situations when it cannot reach steady state. These will be transient, and we have a whole chapter to talk about transient processes. Okay, so in this chapter we are going to talk about a number of different combinations. First of all, we'll talk about heat transfer through single layers, like the slab is a layer and the cylinder, heat transfer through the cylinder, and likewise for sphere. Okay, and then after we do single layers, then we do multiple layers, where it's the same thing but in multiple layers, or the same type of geometry but different materials forming layers. And then finally we're going to do the presence of heat generation. And notice that all these three we will do in 3 different coordinate system. Okay, we're not going to do all the situations, so we'll do some of them and we will not do others that I expect you to complete. So here are again few introductory comments. Why are we choosing this slab, cylinder, sphere? So here is a situation that looks nothing like a slab. So this is the prostate gland that we would like to do cryosurgery upon. So this is the cryoprobe that brings in very low temperature, like minus 196 degrees centigrade. And so I want to freeze the prostate tissue to destroy it. But I don't want the good tissue, good surrounding rectal tissue to be destroyed. So one idea suggested years ago by Professor John Bischoff of the University of Minnesota in his paper is to put a layer of silicone insulator in between the tissue that you're freezing and the good tissue. So this complicated situation can be simplified as you have a prostate on one side that needs to be frozen, and then good rectal tissue on the other side that needs to be protected, and in between you have the silicone insulator. So you have things like something like this. You have a warm side, cold side, and in between you have silicone insulator. And now it looks like heat transfer through a slab. So we may be able to simplify as heat transfer through a slab. Not always we can do it, but we may be able to do this. So again, some general comments. We are going to do slab, cylinder, sphere. If we look around, nothing looks like a perfect slab, cylinder, or sphere. So these real world situations we're going to approximate as the slab, cylinder, or sphere, but this approximation requires intuition, understanding of the physics. When can we do this approximation and when we cannot? And that intuition will come from understanding the physics of these simpler systems, which are much easier to understand. So we understand this first, and then we think of how a real world can be simplified as the simple one. This simplification is the job of the engineer, and this is as of today, this cannot be automated. This is why we need the intuition to be built.